I will switch to English. Okay. So the reason why this course is in English and you are in L2, you're like, hey, we're supposed to have classes in French and stuff. But after next year, so in the master, everything will be 100% in English. You didn't know that, right? It's Université de Strasbourg. You're like, vive la France. But, you know, unfortunately, scientific research and also a lot of education in chemistry is all done in English. And there's a huge problem you will encounter when you go from the bachelor to the master. You will have a barrier to switch. So the faculty, it's not my decision, but the faculty has decided to do a few courses already in L2 in English. So I understand this is going to be more difficult for you, so I will try to speak very slowly and clearly. And as a bonus, everything will be recorded. Everything will be translated en français with subtitles. So you will have on Moodle after the class, okay, not immediately. You'll have the video with the subtitles also in French. Sorry, if you have a question, I'm like semi-deaf, so you have to really shout. Okay.
It's not a question, I say just we need to defend our language. So
of course. I can try to do it in French, but I can't really. So, I mean, you Sure. So in the good old times, you know, in the good old times of Jean-Pierre Sauvage, Nobel laureate, Jean-Marie Lehn, Nobel laureate, there were many scientific papers written in French and in German, and even before in Latin. But since the last, let's say 30, 40 years, 90% of all science is done in English. So to give you the chance to adjust, we're going to do the course in English. You can still ask questions in French, okay? It's okay. On the exam, you have the right to write in French or in English. You can choose. Everything is good. So we'll try to make it, so we'll try to make it as dynamic as possible. And please, if I go too fast, just tell Professor Hermans, you know, I don't know what you are saying, which is okay. So there will be a Moodle page that I will make after this class. If you have questions, you can contact me by email. Any questions you have already now? No, about the course. So I will tell a little bit about myself, professionally, of course. So I am originally from Belgium. I'm Flamand. So als iemand Nederlands praat? Okay, no one. So no, some years there's one person that understands what I just said. So my first language is Dutch, and my second is English, and my third is Spanish, and my fourth is French. So if you want to discuss in Spanish, also cool. And so I did my, I studied in the Netherlands, in Eindhoven, and I studied chemical engineering and chemistry. And then I did my PhD in supramolecular chemistry and in biomedical engineering. And I did a postdoc at Northwestern University in Chicago. It's a great city. If you can go, it's really nice. And since 2013, I am in Strasbourg. I'm in an institute called ISIS. It's a bad name, but it's a good institute. It's just here. I always forget. Here, behind. And we work on systems chemistry. Anyone heard of the field of systems chemistry? No one. That's normal. It exists about 10 years, okay? So it has not made the way from research into textbooks, into, you know, bachelor level textbooks. And so most of the things you're learning now are well, a bit outdated, but that's good. You need to learn the basics. And so systems chemistry, and there, just want to point your attention to this link here. So there's this syschem.unistat.fr. It's a graduate school. What is a graduate school? It's weird. So after the bachelor, you have the master, right? After master, you have the doctorat, the PhD. And so this graduate school, it's a new concept since 5 years in Strasbourg. It takes the bachelor and the PhD, or sorry, the master and the PhD together, and it makes one huge curriculum of 5 years. So and it's all about systems chemistry. So CSE stands for complex systems chemistry. And okay, so you can check that out. We actually enroll people from the bachelor in chemistry. So you guys, next year you have 1 more year, but then the year after, you can consider enrolling in this program. It's really great. Should check it out. So a little bit about systems chemistry. So systems chemistry is a new field, and it comes, well, it's a bit inspired by systems biology. Maybe you have heard about systems biology. That exists 30 years. But in general, what is of interest is systems thinking. Anyone do you know what is systems thinking? Okay. Yeah, sir. This is my first time teaching in the bachelor, so I have to kind of grasp a little bit what's going on. So let's say we look at cause and effect. It's also some English vocabulary. Cause and effect. Okay. So who can tell me a cause and an effect? Very simple. I kick a ball, that's the cause, and the effect is the ball flies away. Simple, right? Now, if I kick the ball harder, what will the ball do? Fly away harder, right? So what most people, including you guys, are thinking most of the time is that the cause and the effect are proportional, right? I increase the cause, the effect also increases. Now, many things in our world are nonlinear, right? So you can have an increase, a small increase in cause and a huge increase in effect. This can be nonlinear. It's called amplification or autocatalysis in chemistry. So you can have nonlinear responses. You can even have what's called negative differential response. Looks okay. Okay, so cause and effect. Sorry, I'll try to look for the other microphone the next time. That's what you think normally, right? I increase the cause, the effect increases linearly. All good. It can be like this. Sorry, that was also nonlinear. But it can be even more complicated, like this. You can first have an increase, and then if you push even harder, you can have a decrease. So let's say the example of the ball, I kick it harder, it goes faster, and kick it even harder, it goes faster. I kick it at the speed of light, the ball will vaporize and everything will be gone, right? That's a hypothetical example, but it could happen, right? So systems thinking is being aware that the world is nonlinear. Think about climate, global warming. Is that a linear process? No, it depends on many, many, many things. And so you need to be aware that there are things that are nonlinearly coupled in networks of things that are interacting. And that's basically what systems chemistry is doing at the chemistry level. So in your body, you have metabolic networks and all kind of complex interacting reactions. And what do we teach you in chemistry? Oh, you have this compound A. and you do a reaction. It goes to B, you purify it, you're happy. Okay, that's cool. It's very important. But in systems chemistry, now we say, okay, now we have a network of reactions, and we're putting it outside of the thermodynamic equilibrium. You will probably get a class on thermodynamics where they tell you about pistons and heat engines and stuff like that, which is all very nice and very important to learn. But in the real world, you know, we are a non-equilibrium system. Your body is a non-equilibrium system. You eat food, you breathe oxygen to keep all these chemical processes going. And these chemical processes control all the interesting stuff you do, like sitting here in spectroscopy, right? So, okay, so short summary is systems chemistry is really cool. Should definitely check out this program. It has very cool classes. And on top of that, which is you don't get in any other master, okay, you get soft skills training, like how to present, how to be a leader. What does that mean? Okay, leadership skills, management skills, all kind of business skills, how to do startup companies and stuff like that. So it's a very dynamic master program that you should definitely consider when you are doing your choice for the master. Like, you want to go physical chemistry or more this or more that, please consider this program. It's very nice. Okay, but down to business. So today will be a broad kind of introductory lecture, and I hope we finish a little bit on time. Hey, I already said this. Okay, so my PhD, Netherlands, then postdoc. I did also chemical oscillators, which is systems chemistry. It's really cool. And now we're doing systems chemistry, non-equilibrium self-assembly. That's a little bit ahead of you, and microfluidics. We're on Twitter, follow us. And this is the group currently. Okay, so enough about me. The course. So we are going to talk mostly about things with light. So we're going to talk a lot about absorption and emission, some vibrational stuff like infrared, some nuclear magnetism stuff, and mass spectrometry. And we'll do a bit of confocal and super resolution microscopy. So it will be 18 hours of CM and 18 hours of TD, I think. So the TD will be by Professor Samori, Professor Ragazon, and Professor El Bayet. This was funny. Okay, you know him already. Okay. Okay, you know him. Okay, yeah. Okay, okay, interesting. Okay, so to warm up our brains a little bit, we're going to do a little quiz. So this course will be a bit interactive. So you all have smartphones. So you can all start scanning that stuff. Okay. Maybe I should do this. Okay. Okay, I will switch to the okay, so you can go to menti.com and then enter this code if you were too slow to scan the QR code. Okay. So please all go to menti.com. I will also go there. Okay, you enter this code 5653042. Okay, so you can put a range of words and then you can press enter. Okay, so matter is a thing, right? It's like, you know, water is matter, paper is matter, like anything liquid, solid, gas that light can interact with. Okay. Let's wait a little bit. So emission, diffraction, refraction, yes, absorption, convection. Okay, yeah. Okay. So emission and refraction are the most popular for the moment. Polarization, yeah, that's good. Okay. Yeah, we're getting a lot of them. Okay, well, I think we have the main ones. Okay, we can keep switch back to the slides. So yeah, so the main ones, some of you already guessed them, is transmission. This is a block of, let's say, whatever it is, glass, water, anything transparent. You can have transmission, reflection, refraction, so the angle changes, diffraction, okay, scattering, absorption. Those are some of the basic ones. And so this course we will mainly look at what happens, because these things are less, well, they're also interesting in optics, but in spectroscopy, these are a bit less interesting. We'll mainly look at what happens to absorption and also what happens after absorption, right? So once, what do you get? You absorb light, and then what happens? You have a molecule, you shine light on it. Does it get a tan, just like people, or what does it do? Well, that's what this course is about, but it has something to do with energy levels and stuff like that. So we'll see what that does, but we can have things like excitation and emission. Okay. So let's look at some general concepts and notions. Okay, this I just pulled from a book, which is a, yeah, question. Sorry. The slides will be on Moodle. So I will put them after the course, right? Because if I put them before the course, then you will all look at them and you'll be like, oh, this is so easy. And then you don't come. So, okay. So you should come definitely because it's nice. Okay. So this is from a book. It has, I mean, this is, you don't have to memorize the slide, but you will at some point, and especially in the TD, you will need to do some calculations. You have to do exercises and you will need all these physical constants, right? So, I mean, most of these you probably know, like Avogadro's number and, Boltzmann's constant and Planck constant. And so these will be important in this course. And many times you will see some kind of equation. What's the first thing you always need to do when you use any equation? Units, exactly. An equation, if you don't check the units, you might be, 10 to the 15th wrong, which can be a problem. And the reason is that we are in Europe, so we use SI units, which are the best ones. But in the US, they use this weird imperial units like, feet and pounds and, crazy stuff. So sometimes you need to convert things. So I'm putting here a conversion table, right? So this is from to. So for example, 1 electron volt, and we will use this one a lot, is 1 times 6 to the minus 19 joule. And then we also use kilojoule, which is 1000, right? And then kilojoule per mole, you have to divide by Avogadro, okay? So for clarity, I just take the one that we are going to use a lot. So 1 electron volt is so many kilojoules, is so many kilocalories per mole, is so many inverse centimeters, is so many Kelvin equivalent temperature. It's not real temperature, it's equivalent temperature. Okay, so this is just, we'll go through some examples and you will need this to keep this in mind. Yeah. Yes, that is a good question. And we'll come to that very soon, actually, on the next slide, I think. So there's this relation, right, to convert wavelengths and frequencies. Okay, so we have the speed of light in vacuum, which is 3 × 10⁸ meter per second. So I'm already doing the kind of scientific notation, so if I write, I guess you know this, but just to be sure. So meter second minus 1 means meter per second, right? Times second minus 1. Okay, it's just more convenient, I think. Okay, so we have speed of light, we have the frequency of light, and we have the wavelength of light. And for example, so if we want to calculate the frequency of light of 400 nanometers, we need to take, we have the frequency, want to know the frequency, which is nu, which is the Greek, it's not V, right? It's nu. Right. Like a weird little thingy, okay? It's a Greek letter. So we have nu and we have lambda, right? So if you want to know nu, we have to divide the speed of light by lambda. And so we need to put the speed of light in meter per second and lambda wavelength in meters. So nanometer is 10⁻⁹. So 400, 10⁻⁹ is 4, 10⁻⁷. Okay, so then you get the frequency 7.5 10⁻⁴ hertz. Hertz means 1 per second. Right, 1 hertz is like this. Well, more or less, I didn't time it, but I guess something like that. Okay, so when we go to spectroscopy, there's this huge range of wavelengths and frequencies that we can look at. So this is from Wikipedia, but it's, I think, very nice. And so you have frequency in hertz, and we have wavelengths in, in different units. You have angstroms, nanometers, micrometers, centimeters, meters, right? And there's this huge range that can be used, right? And so in chemistry, we like being, in the visible, because we can do UV visible and we can do IR infrared, and you can do some microwave chemistry. You can accelerate reactions there. You can do NMR, stuff like that. So depending on the frequency, but just look at the scale just to appreciate how much difference there is. This is 0.1 angstrom, which is really, really small. And we have here 1 kilometer. That's the difference in wavelength. So you are probing very, very different things with these different spectroscopies. So molecular phenomena that correspond to these wavelengths, if you look at gamma rays, you can probe the nucleus of an atom, right? If you are an X-ray or somewhere there, you can ionize things, that's usually, these are very bad for your health, these kind of things. With UV and visible light, we can probe electronic interactions or electronic levels inside atoms or molecules. If we go more to the red, so longer wavelength, we look at vibrations, right? Molecules vibrate. If you look at a molecule in water, it's not just, like this. It's like moving a lot, right? I'll show you some movies later in the next class. If we look at even longer radiation, we look at rotations, or even larger, we look at nuclear magnetism. So there will be one part of this course will be on NMR, which is very important in chemistry, probably the most important. Okay, oops, this I didn't do very well. Okay, I messed something up here in my presentation. But there's this very old discussion, of course, and you probably know about this, whether light is a particle or a wave. Okay, so what do you think? Who thinks particle? Who thinks wave? Who thinks both? Yeah, okay. Sorry. So I screwed this up. 1 second. Oh, okay. I didn't screw it up. So there are older theories considering light as waves or as particles, and many of the things like reflection, you can rationalize it with particle or wave, right? It just comes and bounces. That's fine. But for example, interference, if you have two light beams and you get interference, you get lighter and darker spots. So particles cannot, cancel each other out. That's weird. So, for example, interference, you cannot explain it with particle behavior, and also diffraction or polarization would be difficult. Okay, so along comes Mr. Einstein in 1905, and he actually says, okay, no, it is not exactly a particle, it's not exactly a wave, it's something in between. It's a quantized wave, it's a photon. So photons are what we're going to talk about. So this is a schematic of a photon. So it's a little wave packet, a quantum of light. So this is the definition. It's a massless, so no mass, no charge, stable particle, and it represents a quantum of light or any electromagnetic radiation. So light, we only call it in a very specific, frequency range. But broader is just electromagnetic radiation. Okay, so a photon has a certain energy, right? So the energy of a photon, you can calculate it, right? And you need Planck's constant. So I'm giving it here in 2 different units, because remember the table I gave you, depending if you use Joule or if you use electron volt, these things are quite different. But if we calculate, so for the photon of 400 nanometers, if we calculate the energy of that photon, it is 3.1 electron volt. Okay, you think that's a lot or not, or it's good? We have no idea. Yeah, that's normal. We'll see how we can rationalize if that's a lot or not. Okay. Okay. So if we look at different light sources, so we say a beam of light or a ray of light, it will consist of a flux of photons. So flux means like a stream of things, so flux can be, can be electrons, can be photons, can be anything. And so we're talking about a flux of photons. So what's different here? So there's some flux of photons, and what's the difference between those two?
The first one is organized.
Yeah. That's what. Yeah. So the first one is organized, and the second one is kind of random. Yeah, that's good. So there's a specific name for that. So the bottom one is what's called incoherent light. So you have photons that don't have the same frequency or phase or direction even. Right? So most light that you are used to is incoherent. Like these lights, they all just, the light just goes everywhere, right? So it's convenient for looking at, things in a building. The top one is like what you see in lasers. So a laser will have coherent light. So it means all the photons, they go at the same frequency. They have the same phase, right? And they have a constant phase difference. Okay, we don't really care about that too much yet. But it's very important to consider those different types of light sources. And also, as you know, of course, lasers can have way higher powers than most incoherent light sources. Okay. Okay, so we talked a little bit about light, and now we're going to see what do we need to get a transition between energy levels. So I'm sure you had classes already where you looked at the energy levels inside atoms. I see some people, yes. Okay, that's good. Okay, so the first condition, so you need that one, but it's not enough, right? Is that the energy of the photon is roughly the same as the energy between the energy levels that you're trying to probe, right? So in a way, I find this a cool analogy, is spectroscopy is kind of applied quantum, physics. Because, using quantum theory, and if you really want to go all crazy, we're not going to do that. You can pick up a book on quantum electrodynamics. It's what Richard Feynman and, well, other people, Einstein, Dirac and stuff, have done, because there's the classical description of light, which is about electromagnetic waves. And there's the quantum description of light and matter, like Schrödinger equations and stuff. Did you get the Schrödinger equation? Yes, no? Is that a yes? It's a mixed yes, a little bit. You've heard about the Schrödinger. Okay, so there's the Schrödinger equation, which is super powerful, but no one can solve it except for hydrogen. Hydrogen is important, but anything bigger than hydrogen, that's it, right? So you need other things. But the quantum description is one thing. The classical description is another thing. And what we are going to do in this course is what's called a semi-classical description. So we're going to say light is classical electromagnetic wave stuff. And matter, we need some quantum descriptions. But basically, you have been taught about energy levels in molecules, right, which come from the orbitals and how things hybridize and stuff like that. So basically, with spectroscopy, we can probe the differences in energies between those energy levels. Yes, no, abracadabra, it's good. Okay, if you do, if it's too fast, just tell me. Okay, so that's called the Bohr frequency conditions. Okay, we don't care, but we're going to look how that works. Okay, so Planck constant, mu, is delta E, and delta E is the difference in energy between the higher energy level and the lower energy level. So I call this E upper and E lower. So if you have two energy levels, there's some difference in energy between them. And for example, a photon can come along, it can hit this lower energy level, and it can bring that thing up. What is this called? Absorption. Yes. I will show later. It's actually stimulated absorption. Stimulated because you have a photon that's doing it. Once it's in the excited state, right? So some molecules are very excited. So once you're in the excited state, it can decay and it will emit a photon. That's spontaneous emission, because there's also stimulated emission. So, okay, here are the names. So stimulated emission is you use a photon to kick that thing down and give you two photons. Okay, that's stimulated emission. That's very important in lasers. So in lasers, you use light to create more light, and then those two photons that come out, they have the same phase, they are the same coherence. So that's how you make coherent light. Okay, so we have absorption, stimulated absorption, and we have spontaneous emission or stimulated emission. Okay, that's the first condition. So your photon needs to have the same frequency, right, as the energy level you're trying to probe, the difference between those. The second condition, and this one is way more difficult, and we're not going to go into that today, is that this transition, so you have to first absorb a photon, and then this transition should be allowed. That's weird, right? I mean, molecules can allow or disallow things. Well, yes, apparently. So some transitions are allowed or not, and you can check that by using selection rules. And so these selection rules, there are different ones for atoms. So there's this Russell-Saunders approximation. And for molecules, there is group theory. And more generally, there's this Frank-Codon principle. And maybe or not, we will get into that. But I'm just putting a little example here. You don't know what this means. But here, there's a ground state with different energy levels, different wave functions. And so, for example, this Frank-Codon principle says that you're only allowed to go from the ground state up to whatever state is here, and you cannot go to any state you want, right? So a lot of molecules or even atoms will have many energy levels, and transitions between those energy levels is not always allowed, even though you have a photon which has exactly that energy, right? So the photon needs to have the correct energy, and the transition should be allowed. Okay, so then once we absorb the photon and it's allowed, we are in the excited state. Okay, so the definition is any state higher than the ground state. How can you excite molecules? I mean, we talked about light. What other ways can you use to bring molecules or atoms to their excited state? Heat. Yes. Which other one? Electricity. Yes. So, of course, LEDs, light-emitting diodes are electroluminescence. You use electricity to directly make light. How is that different from the old-fashioned lamp? You don't know these lamps anymore. But before your time, there were these things, glass things with a wire inside that got hot, and they would emit light. Okay, it's different. Heat is also a way to excite atoms or molecules. So if you have ever, you have all seen fireworks, 14 juillet, puff. You see colors. Why do you see colors? Because they have all kind of usually metal salts, right? Barium, potassium, strontium, all these kind of things that when they get hot enough, they can go to their excited state. And when they emit, they have nice little colors. Okay, so light, electricity, and heat. I'm going to tell you a little bit later why heat, you need a lot of heat, like a really hot flame like this. Under normal laboratory experiment, conditions, you will never, or it's not very efficient to excite molecules like that. Okay. So what transitions do we expect? So if you look at the hydrogen atom, and you have these different energy levels, which are drawn not at an equal, it's just random spacing. They're not spaced like that, and you can see that there are all these little lines, and there's all these little names here. So there was this Mr. Lyman and Balmer and Paschen, and all great. It's kind of historic, these names, but basically these people found different, absorption and emission lines of just hydrogen. And so you can see there's many wavelengths, and they range from, this one is the longest and the highest energy, so the shortest wavelength. So the shorter you go in wavelength, the higher the energy is, okay? you go from 94 nanometer to 1094 nanometers. So converted to electron volts, that is 13 to 1.13 electron volts. And just to remind you of the visible spectrum, so 94 nanometers is UVC at the borderline. It's really, really deep UV light. And 1094 is infrared, right? Okay, so now the question is, you see that these transitions, the lowest transition, so the minimum energy you need to do anything in hydrogen, let's say that's our model system, is 1.13 electron volts. So if you have any less energy than that, you're going to do nothing with an atom, right? So for electronic transitions, so between energy levels, you need at least one or several electron volts. If you talk about vibrations, so molecules just do, flappy things, that's much lower energy, right? So vibrational transitions are maybe 0.1 electron volt or lower, right? So much lower. So if you have a molecule in a solution, which is your most used state in chemistry, you will get vibrations, but you will not spontaneously get electronic transitions. Okay, so now we're going to do a little calculation. So we're going to look at, this is the Boltzmann distribution. Probably heard about this. So Ludwig Boltzmann, he wrote this equation, which is very famous. And you can basically calculate the distribution of molecules in a certain state, or it can be, electrons in an energy level or whatever you want. And so you want to calculate the number of molecules with this higher energy, so let's say the excited state, versus the number of molecules that are in the lower ground state. So this equation says that that ratio is e to the power minus this energy difference between those two energy levels times Boltzmann times temperature. Right, so this is the Boltzmann constant that I showed on the one of the first slides, that often they write it like KB, K Boltzmann. And so we're going to calculate this. So this is now very important. So at room temperature, right, so we are 298 Kelvin roughly. And if I want to get a transition of 1 electron volt, even though we're going to calculate it in joule, just to confuse you. So 1 electron volt, remember, is the minimum energy you need to get electronic transitions. So this is to estimate what the probability is that you will get an electronic transition at room temperature. So if you calculate that, so we put delta E is 1 EV, which we multiply by this factor to get joule, and then we have Boltzmann constant temperature, and we calculate that, we get 10 to the minus 17. What does that mean? Not so many. Yeah, that's an understatement. 10 to the minus 17 is like nothing, like really nothing. I mean, very you're very, very polite. So yeah, so the number in the, here, right, just to remind you again of these energy levels. So if I have the number in upper divided by the number in lower, and it's 10 to the minus 17, it means that everything is in the ground state. So this means at room temperature, in solution, you will never, ever have any electronic transition spontaneously. Just will not happen. Now, if we go back to this vibrational things like infrared and vibrations, rotations of molecules, they are 10 times lower energy. Now we come back to our nonlinear. Yeah, sorry.
But the numbers you compare to Avogadro's numbers is small.
Right. Okay. So this is.
If we have, for example, 1 mole of oxygen.
Right. So here, I mean, if you have number of so if you have number of molecules, I can convert this to moles, right? So if we would multiply both with Avogadro, but it will not change anything because you would do the same multiplication on top and on the bottom, so it will just fall out. So it's like you can see it as a fraction, as a probability.
No, I mean for 1 mole of oxygen in the pressure, there will be like 1 million. They are in the
Right, but on the compared, so it would be 10 to the 23rd molecules. So it would be 10 to the 6th of those would have some probability of going to the excited state. So it would be still, the same ratio. So if you have, let's say, you have a spectroscopic technique, you would need to be like so incredibly accurate to detect that one tiny event. It actually, so there are situations where it can be different. In very, very tiny volumes, you can get couplings between molecules and what's called vacuum fluctuations, which then you have to look at what Professor Abbeson is doing, but you can get spontaneous emission even without absorption. But it's, okay, in general, it will not happen, but there are exceptions. It's true. Okay, so the basic point of my story is that these electronic transitions are very rare to happen at room temperature. Whereas vibrations or rotations, they will actually happen spontaneously. Okay, so we're going back to our quiz. You can whip out your phone again. It's the same page as just now. So if we want to get electronic transitions and we want to get the same number as before, so when EV was 0.01, we had this distribution of n upper over n lower of 68, 0.68. So what temperature, you need to do some quick calculation, do you need? Okay, I will go. Okay, there's a lot of interesting puppets. So this one is with points, you have to be fast, okay? Oh, sorry, you don't have the equation. Thirty seconds left. Oh, you guys don't know the Boltzmann constant? Oh my God. Wait. Oh no, it's okay. I should put longer than 1 minute. Oh. Maybe someone. Okay. You all guessed way too low, right? Okay, so for next time, I will put 5 minutes or something. Sorry. I thought you guys were just going to wildly guess, which was my idea, but yeah, so, okay. Sorry. So Boltzmann. That's why you need this table, right? 6 points, where is it? No, 1.38, 10 to the minus 23, right? Okay. Let's look at the units also. Boltzmann, joule per Kelvin, right? Okay. So 1 electron volt in joule is 1.60 10 to the minus 19. Okay. Uh, 60. Okay. So yeah, okay, sorry, I was a bit too fast. So you plug that in, divide by Boltzmann times temperature in Kelvin, that's joule times Kelvin. Okay, we're good, and then you get dimensionless 0.68. Okay. So I'm going to skip the break and we will just finish very early. That's good? Yes, or you need a break? No, no break. Okay. We're going to finish soon, don't worry. Okay. So okay. So one last little thing that you might have never thought about. So when you see colors, and we'll get, the right side thing, we will get back to that in the upcoming classes, is the way you see color. So if you look at a painting, okay, 5 minutes more, guys, and then okay. So if you look at a painting under white light, or if you look at a fluorescent dye or molecule, what's the difference?
Light absorption and what's not absorbed by the matter.
Yeah, exactly.
Matter absorbed from light.
Yeah.
Another
Exactly. So I guess most people didn't hear that. So in the first case, in the left case, which is what you are used to, you have white light, right? This room has white light. What do you think? Do you think this has all the different colors of the rainbow, this light, or not? Yes. We should bring a spectrometer here next time and measure it. But what about sunlight? Sunlight is just uniformly over all wavelengths? No, it's not, right? So you have the solar spectrum, which has some big dips, mainly. Sorry? Yeah, why? Okay, we'll do that on another. So sunlight is more complicated. You have scattering in the environment and stuff like that. Okay, so but in normal circumstances, you are looking at a painting, for example, under white light, and it will have a lot of different colors. And actually, objects that are blue, it doesn't mean they absorb blue. It's the opposite. It's they don't absorb blue, and they absorb all the other colors, and therefore blue is reflected. It goes in your eye, and your eye says blue. Yeah? If you look at red, it absorbs all the colors except for red. If something has white, it's basically reflecting all the colors kind of equally. And if something is black, it absorbs everything. Has anyone seen this color, which is called Vanta black? It's really cool. It's so dark, it just absorbs all the light. Okay. Question. Okay. So in emission, which we'll get to in a couple of classes from now, actually it's different, right? So the color you see is actually the emitted color. So we'll talk about absorbance and then emission, which can be fluorescence. And there's this other thing, which you probably know from when you're a kid. You know, you have some toy, it's in your room, you turn off the light and it glows. That's phosphorescence. Yeah. So phosphorescent, my kid has these shoes that when you turn off the light and they're green. Yeah. That's phosphorescence actually. And that actually is very fun, but it goes by intersystem crossing, triplet states, forbidden transitions and stuff. We'll get back to that in a bit. Okay, so we're going to just finish very early today. It's the first class. So what I want you to remember, right, from this class is there are many types of light matter interaction, right? Transmission, reflection, diffraction, all these things we discussed about. Then very important, this you really need to remember, photons, right, are very efficient to change in between electronic energy levels higher than 1 electron volt. And so you need the right energy of the photon for that transition you're trying to excite. And the transition should be allowed. What that means, we will come back to probably later. There will be a Moodle page. I will make it as soon as possible, where you will have the video with English subtitles, with French subtitles. You can change the speed. You can send me messages with questions. And I will see you on Monday morning. Any questions? Okay, thank you and have a nice day.